This is section 2 of AQA A-level Physics. So, atomic structure. A proton has a relative mass of 1, a relative charge of plus 1, and a mass of 1.6 times 10 to the power of negative 27, and a charge of plus 1.6 times 10 to the negative 19. Neutrons have a relative mass of 1, a relative charge of 0, and a mass of 1.6 times 10 to the power of negative 27, and a charge of 0. Electrons have a relative mass of 0.0005, a relative charge of negative 1, and a mass of 9.11 times 10 to the power of negative 31, and a charge of negative 1.6 times 10 to the power of negative 19. So, these atoms would normally be represented with AZX. A would be the number on top, which is the atomic number, Z would be the atomic mass, and X would be the symbol. Every particle has an antiparticle. This just means they have the same mass but opposite charge. So an electron has a positron, a proton has an antiproton, and a neutron has an antineutron, and a neutrino has an antineutrino, a muon has an antimuon, and a pion has an antipion, and a kaon has an antikaon. Next up, we have the classifications of antiparticles and particles. So these can be split into leptons and hadrons. Leptons include muons, neutrinos, and electrons. Hadrons include baryons, mesons, and baryons have protons and neutrons. Baryons normally have 3 quarks. Mesons, on the other hand, have pions and kaons, which have an antiquark and quark pair. Leptons have a lepton number of plus or minus 1, and these include electrons, muons, and neutrinos. Neutrinos only exist in other interactions, for example, beta decays. Baryons have 3 quarks, mesons have 2 quarks. These are some of the examples. These are some of the quarks, which will normally be given to you in the formula sheet. Next up, we have particle forces. We have electrostatic and strong nuclear. So electrostatic acts between protons, have a nature of being repulsive, and have a range of infinity, and weakens with 1 over r squared, and a strength weaker at short distances. Strong nuclear acts between all nucleons, has a nature of being attractive and repulsive below 0.5 femtometers, and a range of 1 to 3 femtometers, and has a strength of very strong but short ranged. And this diagram sums it up. The force strong nuclear affects hadrons, and the exchange particles result in pions or gluons and has a strength of 1. Electromagnetic affects charged particles, and exchange particles release photons and has a strength of 10 to the negative 2. The weak nuclear affects all particles, with an exchange particle being W plus, W minus, and W0 bosons, and has a strength of 10 to the negative 6. Gravitational affects all particles and has an exchange particle of a graviton, and has a strength of 10 to the negative 39. Strangeness rules. Weak interactions happen if only leptons are involved. Strong interactions happen if only hadrons are involved, and strangeness is conserved. These can create strange particles. And here's an example. Weak interactions happen if strangeness is not conserved. These can destroy strange particles, but total strange changes by plus or minus 1. And here's an example. This is the conservation rule. This just means the result and the product have both the same quarks, baryons, and leptons. So everything is equal and therefore conserved. There are 3 types of decays: beta minus, beta plus, and alpha decay. Beta minus decay is when a neutron turns into a proton. It then emits an electron and an electron neutrino. Beta plus decay is when a proton turns into a neutron. It also emits a positron, the antiparticle of an electron, and an electron neutrino. Alpha decay is when a helium nucleus is emitted, often referred to as an alpha particle. These are some of the Feynman diagrams. So the first one is beta plus decay, second one is electron capture, third is beta minus decay, and fourth is electron-proton collision. They can also be represented by quarks. Next up, we have specific charge. This is charge over mass. So these are some of the examples, as you can see. And photons are packets of energy or electromagnetic radiation which have wave-like properties, and we can use the equation E equals hc over lambda which equals h times f. Annihilation is particle and the corresponding antiparticle colliding, then the masses convert into energy. Pair production is when a photon of sufficient energy is converted into a particle and its antiparticle. Next up, we have quantum physics and more specifically energy levels. Ionization is when an electron is removed from an atom. Excitation is when an electron moves to a higher energy level or a photon is absorbed. De-excitation is when an electron moves to a lower energy level and emits a photon. These can be demonstrated by emission and absorption spectra. This can be obtained by observing what wavelengths are emitted or absorbed by a gas or plasma. So, what we need to know is the order of line spectrum. So this is red, orange, yellow, green, blue, indigo, and violet. Lambda equals C over F. The first example shows 3 possible wavelengths that can be emitted. The second shows 6 possible wavelengths that can be emitted. And the third shows if enough energy is supplied, the atom can be ionized. Demonstrations can be seen in the photoelectric effect, which can be demonstrated by a UV lamp and a negatively charged zinc plate with a gold leaf, or photocell, which is UV radiation incident on a negatively charged plate, which allows electrons to flow to the positive cathode. The greater the frequency, the more kinetic energy the electrons have, as E equals HF. This graph shows that increasing the intensity of the light increases the rate of liberation and therefore current, but no kinetic energy, which demonstrates a one-to-one interaction between photons and electrons. So kinetic energy equals HF minus theta. Fluorescent tubes. So the basic structure of a fluorescent tube is long glass tube filled with low pressure mercury vapor, electrodes at both ends to produce a flow of electrons. Inside surface of tube is coated with a phosphor coating and contains a starter and ballast to initiate the discharge and regulate current. So for this we need to know the types of waves in order. So we have radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X-ray and gamma rays. For wave-particle duality, we have wave-like nature of light is observed when diffraction takes place, when light travels through a narrow slit, and particle-like nature of light is observed in the photoelectric effect as energy is received in discrete packets called photons. And we can use the de Broglie wavelength to calculate particle-like nature.